November 1918, and engineers across Europe are staring at a problem that just won't quit. The Great War has ended, but the lesson is carved into every muddy battlefield from Verdun to the Somme. Wheels alone can't win wars anymore. Trucks get stuck. Tanks break down. And somehow armies need to move men and guns across terrain that looks like the surface of the moon. That's where our story begins, in the strange space between two ideas that shouldn't work together, but somehow must. The half-track concept didn't just appear out of thin air. Back in 1915, a French engineer named Adolphe Cagrès was working for Tsar Nicholas II in Russia, trying to keep the royal family's cars moving through Siberian snow. His solution? Replace the rear wheels with flexible rubber tracks while keeping the front wheels for steering. Simple, brilliant, and it actually worked. By 1919, Citroën bought his patents and started producing the Cagrès-Hinstein system, proving that this hybrid approach could handle terrain that defeated pure-wheeled vehicles. But nobody was thinking about war yet. This was just about getting from point A to point B when nature said no. Then came the 1920s, and military planners started asking uncomfortable questions. Tanks were powerful but painfully slow. The British Mark V crawled at maybe 4 miles per hour on a good day. Trucks were fast but useless the moment they left paved roads. Infantry was still marching on foot like they did in Napoleon's time, which meant armored units would race ahead and then sit around waiting for the guys with rifles to catch up. The Germans, despite losing the war, were already sketching ideas. The Soviets were experimenting. Even the Americans, who'd barely used tanks in World War I, started tinkering with designs at the Rock Island Arsenal. What made half-track so appealing was this wild engineering compromise. You got maybe 70% of a tank's off-road ability, while keeping 80% of a truck's speed and mechanical simplicity. The front wheels gave you decent steering without needing complicated track braking systems. The rear track spread the vehicle's weight across mud, sand, or snow. And because you weren't powering all 4 corners with tracks, the whole thing was lighter, cheaper, and easier to maintain than a full tank. In 1931, the U.S. Army tested the Cunningham T1, basically a truck with tracks slapped on the back. It looked ridiculous. It also crossed trenches that swallowed regular trucks whole. By the mid-1930s, reality was setting in. Germany was rearming despite Versailles Treaty restrictions. Japan was pushing into China with mechanized columns. Spain's Civil War from 1936 to 1939 became a testing ground where everyone learned the same hard truth. Modern warfare needed infantry to keep pace with armor, and they needed to arrive ready to fight, not exhausted from marching 20 miles. The half-track wasn't just a clever invention anymore. It was becoming a necessity. Engineers in Detroit, Stuttgart, and Moscow were racing to solve the same puzzle. How do you build something that fights like a tank, hauls like a truck, and shoots like artillery, all while keeping the price tag reasonable enough to build thousands of them? That question would define the machines that rolled into Poland, France, North Africa, and eventually across half the planet. The hybrid warrior was about to go to war. The Americans approached the half-track problem like they approached everything else in the 1930s, with mass production in mind from day one. While European designers were crafting boutique solutions, engineers at White Motor Company in Cleveland and Autocar in Pennsylvania were thinking about assembly lines that could pump out vehicles by the thousands. The result was the M2 and M3 half-track family. Machines that looked brutally simple on the outside, but hid some genuinely clever engineering underneath those boxy steel panels. Start with the power plant. White Motor settled on the Hercules, JXD inline 6-cylinder engine, a 386 cubic inch gasoline motor that kicked out 147 horsepower at 2,800 RPM. Now, that doesn't sound impressive compared to modern engines, but here's what mattered. It was reliable. It could be manufactured quickly, and mechanics who'd worked on civilian trucks already understood how to fix it. The engine sat in front. Conventional truck style, which meant heat management was straightforward, and you could access it without tearing apart the entire vehicle. Maximum speed on roads hit 45 miles per hour, dropping to maybe 25 cross-country depending on terrain. Fast enough to keep up with tank columns, but not so fast that the ride turned into a bone-rattling nightmare for the 10 infantry soldiers sitting in back. The transmission system was where White's engineers earned their paychecks. They developed a 4-speed manual gearbox with a 2-speed transfer case, giving the driver 8 forward gears total, plus 2 reverse. That range let you crawl up a 60%, grade in first low or cruise at highway, speeds in fourth high, power flowed from the transmission, to a front axle for the wheels and a separate drive shaft running back to the track assembly. The front wheels could pivot normally for steering. But here's the trick. The driver also had brake pedals that could slow individual tracks, letting you make sharper turns than the front wheels alone could manage. It took skill to master, but experienced drivers could practically pivot these things in place. Now the track system itself. This is where American pragmatism really showed. Instead of metal links like tank treads, the M2 and M3 used rubber block tracks developed by the Firestone Tire and Rubber Company. Each track was made of steel cable embedded in rubber with 110 individual rubber blocks vulcanized onto the cable. These blocks were roughly 5 inches wide and shaped to grip dirt, mud, or snow. The beauty of this design was threefold. First, rubber was quieter than metal clanking on metal, which mattered for tactical movement. Second, rubber lasted longer on paved roads without tearing up the highway or wearing out in 100 miles. Third, if you damaged a section, you could replace individual blocks in the field rather than swapping entire track assemblies. The suspension was a modified vertical volute system. Basically, large coil springs mounted vertically behind each of the 4 road wheels on each track assembly. As the vehicle rolled over obstacles, these springs compressed and absorbed the shock. Was it smooth? Not really. Riding in the back of an M3 over rough terrain felt like being inside a cement mixer, but it worked. It was simple to maintain, and most importantly, it distributed the vehicle's 20,000-pound combat weight across enough surface area to keep ground pressure around 10 pounds per square inch. For comparison, a fully loaded truck might hit 40 psi, which explains why trucks sank in mud while half-tracks kept moving. Production ramped up insanely fast once America entered the war in December 1941. White Motor, Autocar, and Diamond T plants were churning out 500 half-tracks per month by mid-1942, hitting 1,500 per month by 1943. Total production topped 41,000 units across all variants by 1945. That's the genius of the American approach. These weren't the best half-tracks ever designed, but they were good enough, and there were tens of thousands of them rolling off assembly lines when armies needed them most. While American engineers were designing for mass production, German designers were obsessing over something entirely different: technical perfection at any cost. The Skafs 251, better known as the Staffs 251 or just Hanomag after its primary manufacturer, represented a completely opposite philosophy, where the Americans said good enough is good. Enough, the Germans said every mechanical component should be engineered to the absolute limit. This made their half-tracks phenomenally capable and absurdly complicated to build. The heart of the Sd.Kfz 251 was a Maybach HL42 TUKRM, 6-cylinder gasoline engine producing 100 horsepower, less than the American Hercules. But here's where it gets interesting. Maybach was the same company building engines for Tiger and Panther tanks, so this wasn't some truck motor pressed into service. The HL42 was specifically designed for tracked vehicles, with careful attention to torque delivery at low RPMs. It pushed the 8.5-ton vehicle to 53 kilometers per hour on roads, actually faster than the American M3, though cross-country performance was nearly identical at around 20 to 25 kilometers per hour. The engine ran cooler and more efficiently than its American counterpart, but required more frequent maintenance and used precision parts that took longer to manufacture. German transmission engineering bordered on over-engineering. The Sd.Kfz 251 used a Maybach Variarex 128 pre-selector gearbox with 7 forward speeds and 3 reverse. Let that sink in. 7 forward gears. The driver would pre-select the next gear with a lever, then tap the clutch, and the transmission would shift automatically using a vacuum system. When it worked, it was smoother and faster than American manual shifting. When it broke, which happened more often, you needed a specialist mechanic and parts that might take weeks to arrive. This is the German half-track story in miniature, technically superior, logistically nightmarish. The track system revealed even more about German design thinking. Instead of rubber blocks on cable, the Sd.Kfz in 251 used metal track links connected by pins, exactly like tank tracks, but narrower. Each side had 70 track links made of manganese steel, shaped with grooves for grip. These tracks lasted forever on hard surfaces and could handle incredible punishment, but they were loud. They chewed up pavement, and they required constant tensioning and maintenance. The Germans accepted these trade-offs because metal tracks performed better in the absolute worst conditions. Deep mud, heavy snow, extreme cold where rubber could crack and fail. But here's where German engineering truly diverged: the interleaved road wheel system. Most half-tracks, including American ones, had 4 or 5 road wheels per side mounted on simple arms. The Sd.Kfz 251 featured 7 overlapping road wheels per side, arranged so wheels from opposite sides interlaced with each other. Imagine looking at the vehicle from behind and seeing the wheels zigzagging back and forth across the track width. This interleaved design distributed weight more evenly, reduced ground pressure even further, and gave an incredibly smooth ride for a tracked vehicle. German soldiers who'd ridden in both captured American half-tracks and their own Hanomags universally preferred the German suspension. It was genuinely that much better. The catch: those interleaved wheels were a maintenance catastrophe. If an inner wheel broke or needed replacing, you had to remove multiple outer wheels first. Mud, snow, and ice would pack between the wheels and freeze solid overnight, especially on the Eastern Front, where temperatures hit -40. German crews spent hours every morning with hammers and blowtorches just getting the wheels unstuck. A task that took 15 minutes on an American half-track could consume half a day on a Hanomag. Manufacturing complexity matched mechanical complexity. The Sd.Kfz 251 required roughly 3,000 hours of skilled labor to build in 1940, compared to about 800 hours for an M3 half-track. Germany produced approximately 15,500 Sd.Kfz 251s during the entire war, impressive for their industrial situation, but barely a third of American production. Quality versus quantity embodied in steel and rubber. Now here's where things get wild. Somebody looked at these glorified trucks and thought, what if we stuck artillery on them? The idea sounds crazy until you remember the core problem. Traditional artillery was towed by trucks or horses, which meant setting up took forever. And moving quickly to avoid counter-battery fire was nearly impossible. Mount that same gun directly onto a half-track, and suddenly you've got mobile firepower that can shoot, scoot, and survive. But the engineering challenges were absolutely brutal. First problem: recoil wants to destroy everything. When a 75mm gun fires, it generates roughly 15 tons of rearward force in a fraction of a second. That energy has to go somewhere. And if you just bolt a cannon to a half-track's cargo bed, the recoil will literally tear the vehicle apart or flip it backward. American engineers working on the M3 gun motor carriage in early 1941 solved this with a combination of approaches. They mounted a French 75mm gun on a reinforced pedestal, welded directly to the vehicle's frame, not the body. Then they added massive recoil cylinders, hydraulic shock absorbers, essentially that let the gun barrel slide backward about 2 feet when fired, turning that violent 15-ton spike into a manageable push spread over a full second. But wait, there's more physics to wrestle with. Every action has an equal and opposite reaction. So even with recoil management, firing still rocks the entire vehicle. The solution was outriggers and spades, metal legs that swung down from the sides and rear with flat plates on the ends that dug into the ground. Before firing, the crew would deploy these stabilizers, essentially anchoring the half-track in place. The M12 gun motor carriage, which mounted a 155mm howitzer on a modified M3 chassis, had a massive spade at the rear that had to be driven into the ground before each fire mission. Without it, firing would literally push the 26-ton vehicle backward several feet with every shot. The Germans took a different approach with their Sd.Kfz 251/9 variant, mounting a short-barreled 75mm gun in a limited traverse mount. Instead of trying to create a full mobile artillery piece, they essentially built an assault gun, something that could roll up with infantry, blast a bunker or building at close range, then keep moving. The limited traverse meant less structural stress because the gun couldn't pivot far enough to destabilize the vehicle. Maximum elevation was only 20 degrees, so this wasn't for lobbing shells over hills. This was for direct fire at targets you could see, usually within 800 meters. Ammunition storage became another nightmare. A standard artillery piece might have its ammunition stacked nearby in a protected position. On a half-track, every single shell is riding along with you, which means armor protection becomes critical. The M12 GMC could carry only 10 rounds of 155mm ammunition internally because each shell weighed 95 pounds and took up serious space. They typically operated with an accompanying M30 cargo carrier half-track following behind, loaded with another 40 rounds. German vehicles faced similar constraints. The Sd.Kfz 251/9 carried just 52 rounds of 75mm ammunition, stored in bins along the hull sides where armor was thickest. Anti-aircraft variants pushed engineering even further. The M16 multiple-gun motor carriage mounted 450 caliber machine guns in an electrically powered turret, creating a mobile flak platform. The entire turret system, including the generator, weighed over a ton and sat high on the vehicle's center of gravity. Engineers had to add counterweights and widen the track stance slightly to prevent the thing from tipping during sharp turns. Fire rate was 2,400 rounds per minute combined, which sounds impressive until you realize that's 200 pounds of ammunition per minute. The M16 carried 5,000 rounds total, giving you about 2.5 minutes of continuous fire before running dry, which meant most of the interior space was just boxes of linked ammunition. The ultimate expression of this concept was probably the Sd.Kfz 251/22, which the Germans developed in 1944. Mounting a 75mm PK-40 anti-tank gun, this thing could punch through 100mm of armor at 1,000 meters, making it dangerous even to Soviet T-34s. But mounting such a powerful gun on a light vehicle created compromises everywhere. Ammunition capacity dropped to just 19 rounds. The gun shield was minimal because more armor would overload the chassis, and firing from anything other than perfectly level ground risked tipping the vehicle. Crews learned to position themselves carefully, knowing that their first shot might be their only shot before they had to relocate or get obliterated by return fire. Tank destroyers represent desperation engineering at its finest. By 1942, both the Allies and Axis were facing tanks they hadn't planned for. German Tigers that shrugged off most Allied guns, Soviet T-34s that overwhelmed German defensive positions, Japanese armor in the Pacific that required more punch than infantry rifles could deliver. The problem was simple. Building actual tanks took time and resources nobody had. Mounting anti-tank guns on existing half-track chassis? That could happen in months instead of years. The American M3 gun motor carriage was literally the first attempt, thrown together in 1941 before Pearl Harbor even happened. Engineers at the Aberdeen Proving Ground took standard M3 half-tracks, removed the bench seats from the back, and mounted a 75mm M1897 gun, which was actually a World War I design, on a pedestal in the cargo area. No turret, no real protection, just a gun shield and a prayer. The crew of 5 stood completely exposed from the waist up. But here's what mattered. It could kill German Panzer IIIs and early Panzer IVs at 1,000 yards. And they built 2,200 of them between 1941 and 1943. These vehicles saw action in North Africa starting in November 1942, where American forces at Kasserine Pass learned brutal lessons about German armor superiority. The M3 GMC's performance in Tunisia revealed the half-track tank destroyer's fundamental problem. It could dish out damage but couldn't take it. The armor was 6.35mm on the sides, barely enough to stop rifle rounds, absolutely useless against anything heavier. German gunners quickly learned that M3 GMCs were priority targets. Knock one out early and you eliminate a serious threat. American after-action reports from the battles around Sidi Bouzid in February 1943 showed that M3 GMCs had to fire from concealed positions at least 1,200 yards back, use their mobility to reposition constantly, and never ever let themselves get caught in the open. They were ambush predators, not brawlers. The Germans developed their own half-track tank destroyers out of pure necessity on the Eastern Front. By late 1943, Soviet tank production was overwhelming German defensive lines. The Sd.Kfz and 251/10 mounted a 37mm P.K.36, which was already obsolete. It could barely scratch a T-34's frontal armor. Desperate for something better, German engineers created the Sd.Kfz 251/22, mounting the 75mm P.K.40, the same gun used in their dedicated tank destroyers. Production started in 1944, and roughly 175 were built before the war ended. This vehicle could genuinely threaten Soviet armor, with penetration values reaching 133mm at 500 meters using standard ammunition, enough to punch through a T-34's hull or turret at most combat ranges, but mounting a gun that powerful on a half-track chassis created vicious trade-offs. The P.K.40 weighed 1,425 kilograms, over 3,100 pounds, just for the gun itself. Add the mount, shield, and ammunition, and you're pushing 2 tons of combat load on a vehicle designed to carry infantry. The Sd.Kfz 251/22 was nose-heavy, handled poorly, and the suspension was constantly overstressed. Maximum speed dropped to 40 kilometers per hour, and cross-country performance suffered noticeably. German crews reported that driving one fully loaded felt like wrestling a stubborn horse. The steering required serious muscle, especially in mud or snow. Tactical employment evolved through hard experience. By 1944, both American and German doctrine emphasized the same principles. Half-track tank destroyers worked best in prepared defensive positions where they could use terrain for protection, engage enemy armor at maximum range, and retreat quickly after firing. The Soviet offensive Operation Bagration in June 1944 saw German Sd.Kfz 251/22s employed in small groups, usually 3 to 5 vehicles, positioned in tree lines or behind embankments. They'd wait for Soviet armor columns to approach within 800 meters, fire a volley, then immediately displace to alternate positions. Survival depended on mobility and surprise because staying to fight meant dying. The American experience in France after D-Day showed similar patterns. M3 GMCs supported infantry advances by providing overwatch from ridge lines, ready to engage German counterattacks. During the fighting around St. Lo in July 1944, M3 crews learned to coordinate with M10 tank destroyers. The half-tracks would bait German armor into revealing positions. Then the heavier M10s would take the actual shots. It was dangerous work with high casualties, but it kept German armor from running wild through American infantry positions. The half-track tank destroyer was never the perfect solution. It was the available solution, built quickly and fielded widely because the alternative was facing enemy tanks with nothing but bazookas and guts. By late 1944, both sides were phasing them out in favor of purpose-built armored vehicles. But for 2 critical years, these improvised hybrids filled a desperate gap. Strip away the guns and the glory, and you find the half-track's actual purpose, getting infantry to the fight alive and ready to shoot. This sounds simple until you dig into the engineering details, because designing an armored personnel carrier means balancing 3 things that actively hate each other: protection, capacity, and mobility. Add too much armor, and the vehicle becomes too heavy to move. Carry too many soldiers and there's no room for ammunition or equipment. Optimize for speed, and everyone inside dies when the first machine gun opens up. The M3 half-track's armor scheme reveals exactly how these calculations played out. The front plate was 12.7 millimeters of rolled homogeneous steel set at a 30-degree angle, which, through the magic of sloped armor physics, provided effective protection equivalent to about 15 millimeters of vertical armor. That's enough to stop standard 7.92 millimeter German rifle rounds at 100 meters and 30 caliber machine gun fire at most ranges. The side armor dropped to 6.35 millimeters, barely enough to stop pistol rounds and shrapnel, but not much else. Why so thin? Weight. Every millimeter of steel across the vehicle's 18-foot length added hundreds of pounds. Engineers calculated that 6.35 millimeter sides were the minimum to keep crew and passengers reasonably safe from fragmentation and small arms while keeping the vehicle light enough to maintain mobility across soft ground. The interior layout was brutally practical. The driver and vehicle commander sat up front in individual seats with armored doors that could swing open. Behind them, the cargo area measured roughly 6.5 feet wide by 10 feet long, with bench seats running along each side. 10 infantrymen sat facing inward, knees almost touching, rifles held vertically or laid across laps. There was a reason for this tight arrangement, keeping soldiers below the armored sidewalls. Stand up and you were exposed from the chest up, vulnerable to everything from rifle fire to shrapnel. Combat-experienced units learned to stay seated until the absolute last second before dismounting. The open-top design was the subject of endless debate then and now. Why not add a roof? 3 reasons: weight, visibility, and escape. A steel roof strong enough to provide meaningful protection would add at least 800 pounds, pushing the vehicle past its suspension limits and dramatically increasing ground pressure. More critically, the infantry squad leader needed to see what was happening around the vehicle during movement. Buttoning up completely meant driving blind into ambushes. And if the vehicle hit a mine or took a catastrophic hit, an open top meant soldiers could bail out in seconds rather than trying to squeeze through narrow doors while the vehicle burned. The real innovation was mechanized infantry doctrine, and this is where the half-track changed warfare beyond just engineering. Before 1940, infantry either marched or rode in unarmored trucks, arriving at battles exhausted or exposed. The half-track created a new tactical option: infantry that could keep pace with tank columns and arrive at the objective ready to fight. During the North African campaign at El Alamein in October 1942, British and Commonwealth forces used American-supplied M3s to follow their armor breakthroughs, exploiting gaps before German defenders could reposition. The infantry arrived fresh with all their equipment, able to dismount and immediately secure objectives that tanks couldn't hold alone. Normandy on June 6, 1944, proved the concept under the worst possible conditions. American armored divisions used M3 half-tracks to push inland from the beaches, carrying infantry through hedgerow country where tanks were vulnerable. The typical drill: half-tracks would advance in column behind Sherman tanks, staying 50 to 100 yards back. When enemy fire erupted, the Shermans would return fire while infantry dismounted from the half-tracks, using the vehicle's bulk as cover. The whole process took maybe 15 seconds, from first contact to infantry on the ground and moving. German after-action reports from Normandy repeatedly noted how quickly American mechanized units could respond to contact compared to their own truck-mobile infantry, who had to dismount farther back and advance on foot. The numbers tell the story of integration. A standard American armored infantry battalion in 1944 had 3 rifle companies, each with 3 platoons, each platoon with 4 squads. That's 36 squads total, requiring 36 half-tracks plus command and support vehicles, roughly 50 half-tracks per battalion. These vehicles didn't just carry soldiers. They carried 50 caliber machine guns, mortars, ammunition, radios, and medical supplies. The half-track transformed infantry from foot soldiers into mounted troops, fundamentally changing the speed and flexibility of mechanized warfare. By 1945, the question wasn't whether to mechanize infantry, but how to build the next generation of vehicles that did it better. Take a machine designed in Cleveland for European battlefields and drop it into the Russian winter or Pacific jungles, and suddenly every engineering assumption falls apart. The half-track's real test wasn't proving grounds in Maryland. It was minus 40-degree mornings outside Stalingrad and 100% humidity jungle trails in New Guinea. These extreme environments demanded field modifications that engineers never anticipated, creating variants that barely resembled the original vehicles. The Eastern Front was where rubber met reality in the worst possible way. German Sd.Kfz 251 started experiencing catastrophic failures during the winter of 1941 to 1942 as Army Group Center pushed toward Moscow. Those beautiful interleaved road wheels that provided such smooth rides became death traps when mud froze solid overnight between the wheels. Crews tried everything: lighting fires underneath vehicles, pouring precious gasoline between wheels and igniting it, even using explosive charges to blast ice free. Nothing worked consistently. German field workshops started welding steel plates over the gaps between wheels, reducing performance but preventing ice accumulation. By late 1942, Factory production incorporated wider wheel spacing and simplified suspension design specifically for Eastern Front units. American M3 half-tracks shipped to the Soviet Union through Lend-Lease faced different problems. The Russians received approximately 1,100 M2 and M3 variants between 1942 and 1945, and Soviet mechanics immediately started modifying them. The biggest issue was cold start capability. The Hercules engine's carburetor would ice up in sub-zero temperatures, making starts impossible without prolonged preheating. Soviet workshops added engine block heaters, insulated fuel lines, and modified carburetors with different jet sizes to compensate for cold, thickened gasoline. They also installed wooden enclosures over the cargo areas, transforming open-top personnel carriers into crude but effective enclosed vehicles that provided life-saving protection from wind chill during long movements. Track performance in deep snow required radical solutions. Standard rubber block tracks would pack with snow, then compress it into ice, destroying traction completely. Both German and Soviet forces experimented with grousers, metal cleats that bolted onto track blocks, digging into snow and ice like climbing crampons. The Germans developed the Winterketten kit, special track extensions that increased surface area by nearly 40%, dropping ground pressure low enough to traverse snow that would swallow wheeled vehicles entirely. Installing these took hours of work in freezing conditions. But units that failed to do so before winter offensives often found themselves immobilized within days. The Pacific Theater presented opposite but equally vicious challenges. Heat and humidity destroyed electrical systems, corroded metal components, and turned interiors into saunas that could cause heat exhaustion in minutes. American forces in New Guinea starting in 1943 faced terrain where half-tracks seemed useless. Dense jungle, narrow trails, swamps, and rivers with no bridges. Yet Marine and Army units found creative applications. Engineers removed the front wheels entirely from some M3s and extended the tracks forward, creating fully tracked vehicles with lower ground pressure for swamp crossings. These field-modified monsters looked absurd but could traverse mud that stopped everything else. Japanese forces encountered American half-tracks during the Philippines campaign in 1944 to 1945 and were genuinely puzzled by them. Japanese military doctrine emphasized light tanks and truck mobile infantry, viewing half-tracks as unnecessarily complex and maintenance-intensive. They weren't entirely wrong. In tropical conditions, the complex American and German half-tracks required constant maintenance. Humidity corroded electrical connections. Jungle mud infiltrated every bearing and joint, and organic material clogged cooling systems. Units operating in these conditions learned to perform twice daily maintenance, essentially rebuilding critical systems every few weeks. Captured vehicles told fascinating stories of adaptation. The Soviets captured hundreds of German Sd.Kfz, 251s during the major offensives of 1943 to 1944. Pressing them into service immediately despite ammunition and part shortages. Soviet crews welded on additional armor plates scavenged from destroyed tanks, creating Frankenstein vehicles that were heavier and slower but better protected. Some Soviet-operated Hanomags received entirely new armament, 85mm recoilless rifles, Katyusha rocket rails, even flamethrowers. The original German engineers would have been horrified, but Soviet doctrine favored maximum firepower over mechanical purity. Desert operations in North Africa required yet another set of modifications. Sand infiltrated everything, wearing out engines in a fraction of their normal lifespan. British forces operating American M3s during the Western Desert Campaign, starting in late 1942, added massive air filters, some nearly 3 feet tall, to protect engines from sand ingestion. They also replaced standard tracks with desert pattern tracks featuring wider blocks for better flotation in soft sand. Water became a critical consideration. Vehicles operating in the Sahara carried extra radiator coolant and often towed trailers loaded with nothing but water cans for both vehicles and crews. The fundamental lesson from these adaptations: the half-track wasn't one vehicle, but dozens of variants, each evolved to survive specific hell environments that would have destroyed the factory standard version within weeks. By 1946, thousands of half-tracks sat in motor pools from Fort Knox to Frankfurt, and military planners were already asking an uncomfortable question: what do we do with these things? The war was over, And in that brutal clarity of peacetime analysis, the half-track's fundamental compromises became impossible to ignore. It wasn't quite a truck, wasn't quite a tank. And in the emerging Cold War world, that middle ground suddenly looked like a tactical dead zone. The Korean War from 1950 to 1953 was supposed to be the half-track's comeback tour. American forces shipped M3s to the peninsula, expecting them to perform like they had in Europe. Instead, Korea exposed every weakness that wartime urgency had papered over. The mountainous terrain shredded transmissions and suspensions designed for European roads. The rubber track blocks that worked adequately in France disintegrated on Korean granite, lasting maybe 400 miles before needing replacement. Maintenance requirements were absurd. A single M3 needed roughly 40 man-hours of upkeep per week just to stay operational, compared to maybe 10 hours for a truck. Commanders started leaving them in motor pools and requisitioning more trucks instead. But the real killer was the tactical mismatch. Korean warfare featured longer engagement ranges than expected, with infantry battles happening at 600 to 800 yards rather than the close-range hedgerow fighting of Normandy. The half-track's 6.35 millimeter side armor that barely stopped rifle rounds in 1944 was absolutely useless against the Soviet-supplied weapons North Korean and Chinese forces were using by 1951. The PPSH-41 submachine gun's 7.62 by 25 rounds could penetrate those thin sides at 200 yards. Heavy machine guns turned half-tracks into Swiss cheese. Commanders quickly learned that using M3s anywhere near the front lines meant dead soldiers. Meanwhile, engineers were designing something genuinely new. The M113 armored personnel carrier emerged from the Ordnance Tank Automotive Command in 1956, and it represented everything the half-track wasn't: fully tracked, not hybrid, aluminum armor instead of steel, providing the same protection at half the weight, amphibious capability. Most critically, it was designed from the ground up as a personnel carrier, not adapted from a truck chassis. The M113 could swim across rivers, survive mine blasts better than half-tracks, and its lower profile made it a smaller target. First production units rolled out in 1960, and by 1963, the writing was on the wall. This was the future. The engineering philosophy had completely shifted. Half-tracks represented 1930s thinking: take proven truck technology, add tracks, and hope the combination works. The M113 embodied systems engineering. Start with the mission requirements, design every component to work together, and optimize for the actual combat environment. The M113's Detroit diesel 6V53 engine produced 215 horsepower, nearly 50% more power than the old Hercules, while weighing less and burning diesel instead of gasoline, safer and more efficient. Its torsion bar suspension provided better ride quality and needed less maintenance than the half-track's vertical springs. Cost analysis delivered the final blow. By the early 1960s, maintaining the remaining half-tracks in U.S. inventory cost more per vehicle mile than buying new M113s. Parts were increasingly scarce since production had ended in 1945. Mechanics who understood the old white motor transmissions were retiring. Meanwhile, M113 production was ramping up with modern manufacturing techniques that dropped per-unit costs below $40,000. Expensive in 1960, but not compared to keeping 15-year-old vehicles running. The international market told the same story. Israel acquired hundreds of surplus American half-tracks in the 1950s and used them extensively through the 1967 Six-Day War. But even they were converting to purpose-built armored personnel carriers by the 1970s. Soviet forces abandoned half-track designs entirely after World War II, jumping straight to fully tracked APCs like the BTR-50. The French kept their half-tracks longest, operating some into the 1970s in colonial conflicts, but primarily because they couldn't afford wholesale replacement. What killed the half-track wasn't battlefield failure. These machines performed adequately in their time. What killed them was evolution. Warfare moved faster, hit harder, and demanded specialized solutions rather than versatile compromises. The M113 and its descendants could swim, had NBC protection, mounted heavier weapons, and most importantly kept infantry alive in an era of ubiquitous automatic weapons and artillery. By 1970, virtually every modern military had reached the same conclusion: tracks or wheels. Pick one. The hybrid era was over. The last American half-tracks left active service around 1964, ending a 23-year run. Some found second lives as engineering vehicles, recovery trucks, or command posts. But the classic personnel carrier configuration disappeared from frontline units. Today, the few working examples reside in museums or private collections. Mechanical fossils from an era when engineers thought maybe, just maybe, they could build one vehicle that did everything they couldn't. But for one desperate decade, when the world needed mobile infantry immediately, the half-track's imperfect compromise was exactly enough.